Buenos dias, chicos. Clovis here. In our last episode, we took a brief respite from the world of functions in order to accommodate a request from a viewer. The concerns of viewers are paramount, especially when it's viewers who at the present time find themselves in high school, where algebra is frequently a matter of concern. However, I would also like to take this moment to acknowledge that might not have been a popular move on the part of this channel to interrupt our work on functions. Therefore, in the episode of today, we're back at it, so let's get on with it. Here go the function from the last time we was concerning ourselves with functions. Now, as we all know at this point, this function is a math statement about minusing 2. Equally importantly, it's a visual image you can put on a graph. And above all, it's a math operation to take in an input and produce an output. Now, as functions go, this one ain't one of the more complicated functions you're likely to encounter. When it comes to math, subtracting 2 from a number and nothing else is definitely on the easy side for many, if not most of us. So we got to take it up a notch. Now, with that last function we no longer looking at, all we had to do was minus 2 from the input. With this function, it ain't so simple. Here we got to do 3 things to the input. First, oh, don't forget, this x is just taking the place of the input till the input numbers themselves show up. So first, we got to take the input, times it by 7. Then we got to minus a number 1 from it. Then whatever number it may be at that point, we got to divide it by 2. Then we get an output. If f of x equals x minus 2 is a minus 2 machine, then this function right here is a times 7 minus 1 divided all by 2 machine. Fortunately, although this function is a good bit more complicated than x minus 2, we can take the same approach in order to put it on the graph. Namely, plug in a bunch of numbers as inputs, get outputs, and put all them numbers on the graph as coordinate pairs and see if a pattern emerges. Time to choose some input numbers. 3, 1, menos 1, 2, 0, menos 2. And definitely not 27 or any number in that vicinity. Why not? Because 27 ain't nowhere to be found on this graph. It ain't gonna help. I ain't making that mistake again. All right, here goes. The number 3 goes in place of the x. 3 times 7 is 21. Minus 1 is 10. Divided by 2 is a number 5. Is that right? 3 times 7 is 21. Divided by 1. No. That's a number 10. 21 minus 1 is 20. Divided by 2 is 10. 1 in place of the x. Times 7 is 7. Minus 1 is 6. Divided by 2. This time I know it's 3. Negative 1 times 7 is negative 7. Minus 1 is negative 8. Divided by 2. I believe that's a negative 4. 2 times 7 is 14. Minus 1 is 13. Divided by 2. I guess that's 13 over 2. 0 times 7 is 0. Minus 1 is minus 1. Divided by 2 is minus 1 over 2. Oh yeah, that's minus 1/2. Minus 2 times 7, that's minus 14. Minus 1 is minus 15. Divided by 2 is negative 15 over 2. And then we graph, because these are all coordinate pairs. All right, 3, 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Dot. 1, 1, 2, 3 on the y-axis. Menos 1. Menos 1, 2, 3, 4. 2, 1, 2. Now remember, sometimes you just got to guesstimate. 13 up top of a 2 means 13 divided by 2, which in turn means 6.5. So 2. 1, 2, 3, 4, 5, 6 and a half. 0 minus 1/2. Negative 2 minus 15 halves, which is minus 7.5. 1, 2, 3, 4, 5, 6, 7, and a little bit more. Once again, a pattern has definitely emerged. But yo, let's connect the dots just to make sure. Yeah. That's definitely a line. Clearly this function and the function of x minus 2 got a lot in common. Guess that's all I got to say about that at the moment. Moving on. Alright, we definitely in different territory now. For one thing, got that tiny number 2 up top of the x. But we still got a strategy at our disposal that's going to work for this function just as well as it did for the last one. Namely, inputs and outputs. In fact, we're just going to use the same numbers. 3 in place of the x. 3 squared is 9, plus 1 is 10. 1 times 1. 1 squared is 1, plus 1 is 2. Negative 1 squared, that's still 1, plus 1 is 2. 2 squared is 4, plus 1 is 5. 0 squared is 0, plus 1 is 1. Negative 2 squared, that's 4, plus 1 is 5. And then, same graphing procedure. 1, 2, 3. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Dot. 1, 1, 2. Menos 1. 1, 2. 1, 2. Up 5. 1, 2, 3, 4, 5. 0. Up 1. Menos 2. 1, 2, 3, 4, 5. Oh, sweat! This functional contraption seemed to kind of got a pattern too. Did you see that coming? All right, connecting the dots. Seemed to look like a letter U, like that one from the alphabet. Well, that is one way to describe it. But this particular function design also got an additional math name. It's called a parabola. Okay, before we conclude, let's skip ahead to a math class scenario. When and if your math teacher introduced this topic in class, it ain't necessarily gonna take them much time to go from here go a function to start with an x squared to any function to start with an x squared is a parabola. So remember that. That ain't untrue. But you ain't gotta try to remember that a function that's got an x squared in the front of it is a parabola any more than you got to remember that a function that ain't got an x squared in the front of it, like x minus 2, ain't a parabola. Because no matter what appearance of function you confront it with, you can always plug numbers into it, inputs, and get outputs out of it. And eventually find out what kind of shape it got. Just like we did just now with this one. That's how we found out it looked like a U. And once you've done that procedure enough times over the course of your math career, with functions similar to this one day, you're gonna just automatically know that when you see a function that's got an x squared at the start of it, it's very likely gonna look like a parabola whenever you get around to graphing it. You ain't gotta take nobody's word for it. And you definitely ain't gotta learn it as a separate fact. Okay, that's it for now. Good luck in math class and good luck with your math teacher. Have a wonderful day. See you next time.